Welcome. My name is Stephen Watt. I serve as the Dean of the Faculty of Mathematics at the University of Waterloo, and it's my pleasure to be the moderator this evening for this Bridges lecture. What we almost saw was an announcement for a conference that will be held here in Waterloo this summer, also going by the name of Bridges. Don't be confused. These are two different bridges. These are like in Königsberg with the bridges. There's more than one bridge, and they take you to different islands. This bridge, that we saw the beginning of an announcement for, is for the Bridges Conference that brings together mathematics and art that will be held at the end of July. So perhaps towards the end, if the AV folks are able to, we might be able to see some detail about that. But it looks like it'll be a fabulous event. It is held all over the world each year at a different place, and this year in Waterloo. It's my pleasure to be able to welcome you here this evening for this Bridges lecture. The Bridges lecture series, I'm going to read its mission statement here, aims to foster discussions across disciplines between mathematics, sciences, arts, and humanities. It is designed to bring us all out of our intellectual comfort zone in a nice, non-threatening way. So, as you can see from our highly polished delivery here, this already so far this evening, that we're relaxed and comfortable here. We see some kind of a new renaissance, just as we saw with Leonardo, the blending of science and art, that it's not the case of interdisciplinarity where you fall between things. It's a case where we have to have people who understand multiple things in order to be able to build these bridges. You can't just have a bridge without having endpoints. And so there has to be some real science or some real mathematics together with some real art. Instead of having a bridge to nowhere, we have a bridge that joins two things or several things. So this is the sixth year of the series. This is the sixth year of the series, and it's actually an anniversary. This is the 20th Bridges lecture, and it's also the 50th anniversary of the Faculty of Mathematics at the University of Waterloo. So numerically significant. Because we have 10 fingers, these are important numbers. It's also the 60th. There are many anniversaries this year, but these two numbers, I think, are significant because somehow the Bridges Lecture Series with St. Jerome's University, with the University of Waterloo Faculty of Mathematics, and the inspiration for the series are all together in some common genesis, and we're very fortunate to see how well it has advanced. Tonight's talk is the Platonic Solids as Tiffany lamps, art objects, and stepping stones to higher dimensions. So open your minds to higher dimensions. Our speakers this evening, I'm going to read a couple of bios if you don't mind. We have Carlo Sequin, professor of computer science at the University of California, Berkeley. His work focuses on computer graphics, geometric modeling, mathematical visualization, and on the development of computer-aided design tools for circuit designers, architects, mechanical engineers, and artists. Hopefully this is multidisciplinary enough for you. Okay. In his recent collaboration with sculptors of abstract geometric art, Séquin has shown how new frontiers can be opened through the use of computer-aided tools. He's a fellow of the ACM, a fellow of the IEEE, and has been elected to the Swiss Academy of Engineering Sciences. He has received the IEEE Technical Achievement Award for contributions to the development of computer-aided design tools, the Diane S. McEntyre Award for Excellence in Teaching, and an Outstanding Service Award from the University of California. So welcome, Carlo. Hans Schepker is a German-born American artist residing in New Hampshire. His work incorporates geometrical and mathematical concepts in lighting and sculpture. He uses disparate materials such as stained glass, origami, paper model building, crocheting, and bead weaving to teach mathematical concepts to students of all ages in public, private, and charter schools in the U.S. and Germany. Let us welcome both of tonight's speakers.
I'm on. Okay. My name is Hans, and as you heard, I was born in Germany, and by training, I'm an electrical engineer, not a trained mathematician, so I'm not hampered by the need for proofs and things like that. For me, it is, if I can build it, it's proof enough. It works. That's how I do it. So that's really how I came to all this. At dinner, I was asked, I think it was dinner, how this whole thing with glass started. I've been building paper models all my life. When I was little, you know, pre-cut sail ships and all these paper things that you can build. You can still buy these models today. It's really fun. And one day, maybe 12, 15 years ago, I wanted to see what happens if I put a light into one of these paper models. Yeah, exactly, nothing. It was just a white blob. It was not what I was looking for. So I cut out little silhouettes of doves, and that was really cute. I had all these doves on the walls. And, yeah, I don't know. That wasn't really still what I wanted. And then I made a cube out of window pane. So all I had was the edges. I put a light bulb in there, and I turned it on, and I saw this cube around me. I was in the cube. That was awesome. That was exactly what I was looking for. And then, of course, I started playing with other shapes and all this, and eventually colors came into it, and you know, the shadows that were thrown onto the walls from the stained glass lamps. They, I don't know what I did. They really made great impressions, and they look very beautiful in all this. So that's how that started. At some point, I went to a math conference. It was, I think, called Math Fest. It was in Rhode Island, 4 hours from my house. That was doable by car. And I was having a booth with all my lamps and other stuff. And I was kind of scared because I was facing, you know, some 1,200 or 1,500 mathematicians, rocket scientists, and all kinds of other people that were talking about things that I had not the faintest idea about. And I noticed, you know, after a few hours that they had no idea what I was talking about. You know, shapes and things, this simple kind of geometry, however beautiful it was not their thing anymore. And the story that I'm trying to, you know, talk about, that I want to come up with, is my meeting with Joshua. Joshua was, I think, a post-grad. He sounded like Brooklyn. I have no idea who he is. I've never met him again. He came to my booth, and he picked up a certain sculpture. And he really, honestly looked at it for like 3/4 of an hour. Looked at it from far, from near, this angle, that angle, and he looked at it from a distance. He put it on the table and walked back, and 3/4 of an hour. Honestly, seriously. And then he put it down and walked away. Didn't say a word. 2 hours later, he came back and said, I figured something out. And he told me. And picked this thing up again, looked at it for another 15, 20 minutes or something, and walked away again. Very interesting fellow. I wish I knew more about him. I would still want to talk with him. But he came back, and I figured out something else. And he told me that too. And I will walk you later in this presentation, after Carlo and I do some other things, through this whole exercise. This is just my introduction to, this presentation. Here's Carlo.
First, some clarifications. I'm also an immigrant, and I'm also not a mathematician. And a little bit more background. I grew up in Basel, Switzerland, where I attended the Mathematisch-Naturwissenschaftliche Gymnasium, which is a high school with emphasis on science and physics and mathematics. And then later, when I was at university, I took my mathematics lessons in this 500-year-old building under the Red Arrow. And in that same building, there were people like Jacob Bernoulli that had taught there, or like Leonhard Euler. So clearly there was some heavy baggage in my past, but I was really fascinated with numbers from an early age on, and I fell in love with geometry in high school, particularly when we had this course in descriptive geometry, where we had to construct intersections between two cylinders or cones with just rulers and compasses. I thought this was really cool stuff, and ever since geometry has been in my bloodstream. So now I'm supposed to tell you a little bit more formal background behind these wonderful creative artistic objects that Hans is going to present. And the first thing we're going to talk about is the regularity. Some of these objects are regular geometrical objects, and what does that mean? Let's start with something simple in 2 dimensions. Regular means that all the vertices and edges in a polygon are indistinguishable from one another. They're all the same angles, all the same edge lengths. Okay? We can start with an equilateral triangle. We can go on with a square. Then we have regular pentagons, hexagons, heptagons, and so on, off to infinity. So there are infinitely many of these regular 2-dimensional polygons. Now let's step into 3 dimensions. You see little sculptures here. These things are called the Platonic Solids. They have been known to mankind for about 2 millennia, and they're also regular because for each one of these objects, every vertex looks like every other vertex, every edge looks like every other edge, and every face looks like every other face. Okay? So the question is, how many of them are there? These were the 5 that Plato knew. Are there any more? Who thinks there are any more? Okay. Who could actually prove to their grandmother or to their grandchildren that 5 is all there is and there is no more? Okay, that's what I'm trying to help you to understand. And I realize I need another prop, so give me a second. So, in order to construct a regular polyhedron in 3D space, we have to cover the surface with regular 2-dimensional n-gons. Okay? That makes them really regular. And so we can ask, what happens? How do we make one of these objects? We need to make real 3D corners. And if we start, for instance, by taking 3 squares and putting them around a vertex here, well, that's not a corner yet. 3 squares in the plane, but if we squeeze out this empty space and we force these 2 edges to come together, suddenly, voila, we have kind of popped up and formed a corner in 3 dimensions. Okay? And that is the trick that by putting 3 squares together, we can make a regular corner, and then 8 of these corners make a cube. We can also take 3 pentagons, put them together around the corner as marked by that little red circle, and then we get a dodecahedron. And so now, we can go and step through all possibilities. We say, all right, let's take our 2D tiles, let's start with the triangles, and we can put 3 of them together, and that would then give a tetrahedron. Or we can put 4 of them together, and then you will get an octahedron. Or we can put 5 of them together, and then that makes an icosahedron. Or we can put 6 of them together. What does that make? Flat kitchen floor, right? So that's no good. Okay, when we go to the squares, we can make the cube, and we go to the pentagons, that makes the dodecahedron, and then that's all we can do with squares and with pentagons, because more than 3 would not fit around that vertex. That would exceed 360 degrees. Okay, what about hexagons? Again, we essentially get a flat kitchen floor. What about heptagons? Well, they don't fit. Or if you put 4 of them together around the vertex, you get some kind of a saddle surface. But then you have 2 concave edges and you have 2 convex edges, and so not all the edges are the same. It would not be regular. So here's the story. We have the whole story. That's all you can do. That's the only way that we can make, Platonic solids. Just for completeness, you can make so-called semi-regular polyhedra, and there you allow to have more than one type of tiles. All the tiles are still regular n-gons, but you can have at one corner a square coming together with a hexagon, and maybe a triangle. That's fine, as long as all the vertices look the same. And with the same kind of reasoning, figuring out all the combinations you can do, figuring out which ones actually work, you can then prove that there are exactly 13 of these Archimedean solids, which are the semi-regular polyhedra. Okay. And with that, that's the first step of mathematical background. Back to Hans.
So, the 5 Platonic solids. We heard that there are only 5 of them. This would be the tetrahedron, a triangular pyramid. And if you look at it, it's all the same from all angles, all sides. Let's stick with the triangles. This would be the octahedron, 4 triangles around a corner. And this would be the icosahedron, 5 triangles around the corner. When you come down later and play with these things, you're all welcome to touch this. This one has a boo-boo. A student kind of set it too hard on the table. So triangles, we've covered the triangles. 6 triangles would just make a floor tiling. Squares, 1, 2, 3 squares around a point. There cannot be more because then it again would be flat. But 8 of these points and you have a cube. And the dodecahedron. Again, 3 pentagons around a point. 20 points, you have a dodecahedron. Platonic solids, why are they called Platonic solids? Plato did not discover these. I think he worked with them. In his days, there were 4 elements, earth, water, air, and fire. And he associated those 4 elements to 4 of these regular solids. This was water, this was fire, this was earth, and this was air. Now the dodecahedron he didn't really know what to do with, I think, and he made that the quinta essentia, or the substance that held everything together, or the some god of his painted the firmament is one of the words that appears in some of these writings, the universe. So that's where these 4 elements come in, and the 5th kind of holds it all together. I have made some lamps in these shapes. I don't have an octahedron as a lamp. I actually don't have a picture of one either. But there's, the tetrahedron, cube, octahedron, icosahedron, and dodecahedron. There's a cube, a tetrahedron, a dodecahedron as a table lamp, and an icosahedron as a hanging lamp. This is a picture of one of my older iterations of a studio. I'm lying on the floor and I'm looking up at the ceiling. There is still no octahedron, a pure octahedron, but up there is an octahedron and a cube intersecting. So they can work together. Thank you. There's an octahedron and a dodecahedron intersecting. I don't know, that's just me playing with shapes. And I can do that because these shapes have relationships to each other. Some of them are outright duals to each other. They are like twins. The octahedron and the cube can be turned into one or the other if you cut off the tips. If you cut them off, keep cutting them off, keep cutting them off, the other one appears in it. So the cube and octahedron are duals, the icosahedron and dodecahedron are duals. Now the tetrahedron turns into its own dual. It will be half the edge length and it will be upside down. It's self-dual. Which movie was it now? Oh yeah, Spaceballs. It's its own twin. So there it is, and that's the ceiling in my, it was the ceiling in my studio. This is a lighthouse that gives me direction, that keeps me straight. It has nothing to do with Platonic solids, not even much to do with math, but keeps me going. Cricket Hill is the dirt road on which we live. So this is the Cricket Hill.
Okay, so what is this fourth dimension? Some people think it doesn't really exist. Some of the people may say it's just a philosophical notion, and then there are other people who say, oh, it's just time, okay? But that's not all there is. Higher geometrical dimensions are actually quite useful, and they do indeed exist. So let me start with a single sort of mathematical point, okay? This mathematical point here is too small, you cannot really see it, but you know where it is, okay? And now we take this point, and through a process called extrusion, we stretch it into a line segment. Can you all see the line segment here? Okay, and now holding this line segment like that. Now, in another direction, we again do an extrusion. We take this line segment, and we extrude it horizontally. And what would we get? We now have a square. Okay? You can all see the square here. And now we take that square, and we extrude it again perpendicular to itself. And what do we get? We get a cube. Can you all see that cube? Okay? And now we take that cube, and again, perpendicular to all three dimensions of the cube, we extrude it again, and we get the four-dimensional hypercube. Now I see some puzzled looks. You say, well, wait a minute. You know, what direction is that? I can't quite see it. And yeah, it's indeed difficult, and maybe we can understand why that's difficult by looking at flatland, which is the poor two-dimensional creatures that can crawl around only in a perfectly flat surface. But they're not dumb, they're still mathematicians. They know about the two-dimensional regular polygons, because even though they cannot see it the way we see it, they can crawl around and they can measure the corners and say, okay, 60 degrees, 60 degrees, 60 degrees, all equal lengths. This must be an equilateral triangle. And so they're very familiar with this infinite series of two-dimensional regular polygons. And then one day, a visitor from our three-dimensional world comes down to flatland and tries to explain to them what is it that we call a cube. This is very simple. You start with a square, and then you just perpendicularly extrude it up. And so in flatland, that's the kind of figure that the flatlander draws. Says, oh, we have a square, and then we go sort of diagonally. Says, no, 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 you're not going diagonally. You have to go up. You have to go perpendicular to that face of the square. And they just cannot do it, and they're very frustrated. And the same is true for us. So we have this cube, and now we need to find a direction that's perpendicular to all three axes of the cube, and we just cannot really point in that direction. And I'm sure out there may be some four-dimensional beings, and they're kind of looking down on us, and they're kind of smiling at our futile attempt to kind of point into the fourth direction. But that doesn't mean it's not there. It's really out there, and it's quite real. Okay, now, in this fourth dimension, we can also have regular solids. We call them four-dimensional regular polytopes. Polytope is just a generalization of the term polyhedron in all the higher dimensions. Now, in 4-dimension, the shell or the crust of this 4D polytope is composed of all the regular 3D polytopes that we had, and that means of the Platonic solids. So the Platonic solids, they're going to be the tiles that make this crust or surface of the 4D polytope. And again, we have to assemble these tiles in such a way that at all corners and at all edges, it always looks exactly the same, and all these cells come together in exactly the same way. So that's kind of cool, we can think about that, but how can we actually see something like that? So we're thinking about ways of making these higher dimensional polytopes visible. Now, I've shown you pictures of the 3D Platonic solids, right? You remember that? Who remembers having seen my pictures of Platonic solids? Cool. But you know, I didn't show you any models like Hans did. I show you two-dimensional figures. And you were perfectly all right seeing them as three-dimensional objects, because our whole visual system is actually just 2D. But there's a process in your brain that takes a good enough representation in 2 dimensions and gives you a 3-dimensional image. What you have seen is projections, okay? A clever way of taking the 3-dimensional object and making an image of it in 2 dimensions that's good enough so that in your brain you can then recompose essentially the 3-dimensional object and find out what's really going on in 3 dimensions. And that is exactly the same approach that we're now going to use in order to see the 4-dimensional polytopes. Here is a shadow of a solid object. Solid object is a cube. Now, if we just take a true shadow as shown on the left, it's kind of a blob. It doesn't reveal very much, and it's kind of not that easy to see that as a cube. But if instead we take a wireframe, we highlight the edges of the cube, and then we project that in the same way down to 2 dimensions, you get the drawing on the right. And that's much, much easier for us to see that, oh yeah, clearly I can see that is a cube. Okay. So, these are sort of the main projections which I'm going to use in order to kind of depict some of these 4-dimensional regular polytopes. On the left, you see 2 oblique projections, one of the cube being projected down to 2D, and then right next to it, it's basically the hypercube being projected with an oblique projection to 3D, and then once more down to 2D so we can actually put it on the slide. And on the right-hand side, you see 2 perspective projections. First, again, the cube, and because it's perspective, the front face is larger than the back face. Okay? And then on the right, we do the same thing now for the cube. The front cube in red is bigger than the back cube, which is blue. And it's sort of shifted a little bit. Okay. And then it's projected once more so that we can get it onto the slide. And so what you can see here, we can actually provide some extra information about depth. In this case, it is color. So red is close, that's up front. You know, the bluish-green cyan thing is sort of the back face, and then the the yellow-greenish lines are the transition from the front to the back. And that gives you sort of an idea what this object actually might look like. Another critical decision is, which is the direction from which we're actually looking at these objects in 4-dimensional space. Now, we can orient our line of sight in such a way that it passes through opposite vertices. As in the top left figure, there's a cube, and it's lined up, so we enter, you know, the closest vertex in the red circle, and the sight line goes out the back end through the opposite vertex. We call such a projection a vertex first projection. The upper line or the upper row shows a parallel projection from that direction, and the one just below shows a perspective view of that. Okay? Then one step over to the right, we can focus our light, our sine our line of sights in such a way that it goes through the middle of the edges, one in the front and then opposite one in the back. We call that an edge-first projection. And then one more over, we can line up with the center of a face and exit our sight line through the back face, and that would be a face-first projection. Below in the lower half, you see exactly the same kind of projections now applied to this four-dimensional cube. But there's now one more thing we can do. On the very right, you see something that's called a cell-first projection. So there we kind of line up with a front cell, and we make sure that from the center of the front cell, our line goes through the center of the back cell, and we call that a cell-first projection. Now, if we do a cell-first projection, where we get really very close to the front cell, then the same thing that would happen with a cube. If I get my eyes really, really close to that cube, then I see the front square, and everything else of the cube is inside that front square. And the same is going to happen if we take sort of a hypercube, okay, and we make a cell-first projection, and we get close enough, then we see the front cell, which is the outer cube, and the whole rest of the cube is all inside. Okay? So that's a sort of a preferred projection because it gives a very nice and regular and symmetric view. Okay, now we would like to find out how many of these regular 4D polytopes are there. Okay? And we're doing exactly the equivalent what we have done before. We're taking a construction where we try to assemble a 4D corner out of 3 or 4 or more of these Platonic solids. So remember, when we did the cube construction, we started out with 3 squares, and then we essentially squeezed out that wedge of empty space, and pop, we got a 3-dimensional corner. Now we're doing the same thing 1 dimension higher. Here is again a figure, but now assume that behind each one of these squares there's a whole cube. Okay? And so these 3 cubes, they're now sharing an edge that goes right through that point here. So in this 3-dimensional thing, there's kind of a wedge of empty space here. There's a face of a cube here, there's a face of a cube there. And again, we're now saying we're going to squeeze out that wedge of free space by bringing this face in contact with this face. We're doing essentially this, and pop. It pops out from 3 dimension and makes a 4-dimensional corner. Okay? So that's the construction. So now we're going to look. Right, you go essentially what we did before around the corner, we're now doing the same construction around an edge. These 3 cubes share one edge, and we're squeezing out, this 90 degree of extra space, and that forces something to bend. It cannot bend in 3D space, it has to pop up in the next higher dimension. Okay, once we understand the principle, now we can look at the various Platonic solids and count in how many different ways can we actually do that. The crucial value now is the dihedral angles in these various Platonic solids. And then we can figure out how many of these can we possibly group around a joint edge, how much free space there is, and the less free space there is, the less bending we have to do, and basically a bigger thing we get, and the more cell we're going to use. So now we look at that little list, we find that the tetrahedron has 70.5 degrees of dihedral angle, so we can certainly fit 2, or 3, or 4, or 5, and they're still not exceeding 360 degrees. Okay, by the time we fit 5 of them, we're very, very close. There's only a couple of degrees left. Okay, and it turns out that for all the cases 3, 4, and 5, we actually get an object that can be replicated so it fills the space and it closes back onto itself, and actually it forms an 4-dimensional regular polytope. If you take a cube, we have a 90-degree angle, and so we can put 3 of them together, as in the example that we had before. If you try to put 4 of them together, there's no space left from bending. We get essentially a 3-dimensional kitchen floor. Okay? So we can only do one thing with cubes, and that is put 3 of them around an edge and make that object. The octahedron, 109 degrees. Again, we can put 3, but not more. Dodecahedron, 116, gets very close to 120, but we can still fit 3 of them around an edge and then have a little bit left in order to close it off. And then, unfortunately, the icosahedron is useless. It has a dihedral angle of 138 degrees. 3 of them is already more than 360, so that is not going to be of any help. So here is now the whole series of all possible regular polytopes in 4D. If you use tetrahedra, 3 around of them gives what we call a simplex. 4 around an edge is called a cross polytope. 5 around them is the big 600 cell. 3 cubes make a hypercube. 3 octahedra make a 24 cell. And using 3 dodecahedra makes a 120 cell. And as I said before, we can do nothing with the icosahedron as a building block. And here now are the first 4 of the 6 regular polytopes in 4D. The first one is the simplex, also called the 5 cell, and it's shown in a cell-first perspective projection. So again, we get one cell, which is a tetrahedron, on the outside, and everything else is kind of crunched to the inside. To the right of that, we see a hypercube, or tesseract, but in a slightly different projection. This now is a vertex-first projection, so the front vertex and the back vertex kind of line up, and so in the middle you get this crossing where you don't just have 4 edges come together, but it looks like, you know, a superposition of 2 vertices, so 8 edges are actually coming together. And then next to it is the 16 cell that uses, 4 tetrahedra around an edge. And to the right, I think that's the most beautiful one. It's the 24 cell that uses 3 octahedra around every edge, and a total of 24 octahedra. And here then is number 5, the 120 cell. It has 600 vertices and 1200 edges. Again, I show a cell-first and extreme perspective projection. That means the front cell is so close that everything else I can see through the front cell. So the outside is a dodecahedron, and then everything happens inside. And it gets very, very crunched up in the middle. So you cannot really see most of it because it's so small, and this 3D printer probably couldn't resolve it. Another option is shown with the last one of these polytopes, the 600 cell, which has 120 vertices, 720 edges, and, sorry, I made a mistake, 720 faces and 1200 edges. In this case, it's a parallel projection, and that means, it is much more regular and round. All the edges are roughly of the same length. But unfortunately, when you do this parallel projection in sort of the cell-first direction, some things are hidden, because just if I were to make a parallel projection of this cube, then the front face would be exactly behind, the front face would obscure the back face, which is exactly behind it. And so you would see somewhat less than half of the edges. You would only see these edges, but not the ones that go to the back and not the one in the back themselves. So in a way, it makes a slightly simpler model. And so David Richter could actually handle that and build the whole thing out of drinking straws. Now, there are many, many, many different ways in which we can make models of these projected 4D polytopes, and you will see, different versions in a very artistic manner shown by Hans. Here are just a few samples, so you get a feel that there may be actually quite different ways where the same object comes up, and it's always the same name, but it looks different. Here again is the simplex. In this particular model, I did something to reveal the inner structure of that simplex. Here are 2 more views of the hypercube. On the left, I have sort of a color-coded perspective view, where the blue is the front cube, and then yellow is the back cube, and then the orange struts go from front to back. Whereas on the right, I have again a vertex-first projection. It makes a big difference from what angle that you're looking at. Here are 4 views again of the hypercube, and on the top there you start out with a cell-first projection. To the right is a face-first projection, and then we go bottom left is a edge first projection, and finally on the bottom right, another cell first projection. All of them with a perspective view. And here is Dali's view of an unfolded hypercube. And the unfolded hypercube is like opening up the net of a cube into sort of 6 squares. In this case, you open up the hypercube into 8 cubes, and so can really see all 8 cells very, very clearly. For me, the 24 cell is the nicest one. That's sort of a view from an arbitrary angle. But if you look in a particular direction, then we can actually see one of the 3-fold symmetry axes of this particular object. And here again is the 120 cell. This time it's made, well, the whole thing is made out of 120 dodecahedra, but we only see about half of them because this time we again did a parallel projection that masks about half the structure. This is one of the very first renderings that I did many, many, many years ago of the 120 cell. Here is a very small model made by Bathsheba Grossman on a Sanders rapid prototyping machine. The whole thing is only about 2 inches in diameter, and so it's probably the smallest physical 120 cell that I know of. And John Sullivan actually made a wonderful rendering using soap bubbles in the same arrangements as the cell of the as the cells in a 120 cell. This is a historic rendering of the 600 cell. Again, it's a projection where you don't see all the edges. And if you go to a very highly perspective cell first projection, then you get this view where it's basically a big tetrahedron on the outside and everything is kind of crunched on the inside. But now let's look at some much more beautiful models that Hans has created.
Carlo, 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 Carlo. Carlo, you're too kind. Right, that's better. Here we go. So, Carlo told you about these different projections of these 6 regular polytopes, and I have made lamps out of 5 of them, and I can show you some of that. The first lamp that I would like to show you here is, and maybe you can see this, can you see this? This would be the first one, the 1, 2, 3, the 5 cell. This is the simplex. The next one would be the 8 cell, this one, which I kind of like. It's a very nice one, but well. And then we have the hypercube here. I probably don't have to show you. You can also come and see that later. And this is also my favorite, the 24 cell, with the 24 octahedrons, octahedra. So, and I made this into a lamp, which I call, here is looking at you fourth. Because, well, we are looking at the 4th dimension, and I included all 4 dimensions. Any place is a point. You know, let's say there's a point. No dimension. There are lines here, edges, and we can draw 2 points on them and we have a line. 1 dimension. This flat base here is possibly, you know, 2 dimensions. Then we can raise it into 3 dimensions, and I have the 3 Cartesian planes in this, you know, the X, Y, and Z plane in this little sculpture in the center here. 3 dimensions. And at least 4 of the 6 4-dimensional objects projected into 3 space. Therefore, here's looking at you fourth. Even I can't see it, but there it is. So, the first 4. Then we have the dodecahedron, the 120 cell. And Benoit was so kind as to build this stick model of the 120 cell. So there are really 120 dodecahedrons in this whole thing. And because of the projection, some of them are flat. You know, this one surface here is a dodecahedron. And they kind of collect themselves up. And I made a lamp, a more artistic rendering of a 120 cell. You know, if you look at that model, and this here, there are not as many surfaces, faces in this as would be in there. How many faces? 720, right? So these are not 720. And but it is my rendering, my artistic rendering of a hyperdodecahedron. I think I have another slide of this. Yeah. No, we are jumping to the 600 cell, which this is one of the possible stick models. There are also tons and tons of edges and faces and all that, but I did not, this model does not have all of them. This is a cell first, I think. But I can see 600 tetrahedrons in there, can't you? Okay. You want me to count them up? Yes, I knew someone would say yes. So, but I cannot have all these faces, all these triangles in a glass model. So I came up with this as a paper model, as a rendering of the 600 cell, which I'm going to build. I don't have the glass yet. So the 600 cell, we have the 4 cell, the 8 cell, the 16, the 24, the 120, and the 600 cell here. And I don't know if you remember back the picture of me, I was holding up this little model of the 24 cell, which is done in straws. Still one of my favorite shapes. So here we go once more to my model of the hyperdodecahedron, which is hanging in my studio, and the paper model right next to it, which, you know, that model over on the end there was designed and built. Here we have 2 more pictures of that model. The big picture and the background picture actually is of my first attempt at the hyperdodecahedron, but I ran out of glass, so I couldn't finish that, and I bought new glass and made this one. These are my 4-dimensional renderings. Yes?
Okay, if you're not afraid, we'll go actually into the 5th dimension and beyond. So in order to go to the 5th dimension and make a regular polytope up there, we need to use our 4-dimensional polytopes, those 6 beasties that you have just seen, as the tiles that make now the crust of the 5-dimensional regular polytope. But when we examine the dihedral angles of these 4-dimensional polytopes, we see that 4 of them are pretty useless. Okay, the 5 cell, or simplex, has 75 degrees. And so we can essentially use 3, 4, or 5 of those to do something useful. The tesseract or hypercube has 90 degrees, and so we're back to this particular game again. We have exactly one option, using 3 of them and going to, you know, pop up a corner in the next higher dimension. The 16 cell is 120 degrees, that will get some kind of kitchen floor. 24 cell, another kitchen floor. The 120 cell, 144 degrees, well, that's beyond, okay, and a 600 cell is even rounder, 164 degrees is useless. So most of the 4D polytopes are too round to serve as building blocks to step up in the next dimension, but we can use 3 or 4 of the simplex, or we can use 3 of the tesseracts. There's just 3 things that we can do to get to the 5th dimension. It turns out, actually, if you continue and look at the dihedral angles of the objects you create there, that in the end, there are exactly 3 methods by which we can generate regular polytopes in 5 dimensions and in all higher dimensions. So, to answer the question, what happens in higher dimensions, how many regular polytopes are there in 5, 6, 7 dimensions, and so on, the answer is relatively simple. There are exactly 3 in each one of these dimensions. Okay? I show some pictures here for 6-dimensional objects, and there are 3 series. The first one is the Simplex Series, and there every one of these has n plus 1 vertices, so in 6th dimension we would have 7 vertices. The hypercube would have 2 to the n vertices, and then the cross polytope would have 2 times n vertices. And let's quickly look at those 3 series and see how they get produced and continue up through all dimensions. To make a simplex, we basically need to take n plus 1 vertices, if we're in n dimensions, and arrange them at equal distances from one another, and then connect every one to every other one. Okay? In 1 dimension, it's just a line segment. In 2 dimensions, we have 3 vertices making equilateral triangles. In 3 dimensions, we have 4 vertices forming a tetrahedron, and so on. The question is, can you always arrange d plus 1 vertices in this manner that everybody has same distance from everything else? The answer is yes, because you can start with the simplex 1 dimension below, and then simply add exactly 1 new vertex above the center of the old simplex in the direction of the new dimension, and just put it up high enough so it has the same distance from the old ones. If you look, for instance, at the right-hand drawing, at the tetrahedron, we have an equilateral triangle, and now we add 1 more vertex above the center of the equilateral triangle, and we just lift it up far enough so it's exactly a unit length away from each one of the corners. And that process essentially continues, and you can do that to arbitrary dimensions. You always get another simplex. That's series number 1. Series number 2, I already kind of showed you at the beginning. We start with a line, we extrude it parallel to itself, make a square, extrude it parallel to itself, make a cube, extrude that one to make a hypercube, extrude that one to make a 5D cubes, and so on. That one also, you can readily see, we have a process that gives us all of those. And then finally, here's a recipe for the cross polytope series. The cross polytopes are essentially the duals of the hypercubes. And one recipe in order to make any one of these is you go in your n-dimensional space. You have 2 n half-axes sticking out in your n dimensions. And you put the vertex exactly 1 unit away on each one of these half-axes. And now you need to connect all the vertices with all the other vertices, except you do not connect the 2 points that are on the same axis, on the same 2 half-axes, okay? And that process will give you all the cross polytopes, and you also can do that, in arbitrary dimensions. So to summarize this, there are sort of 3 polytope types that result through all the dimensions. The simplex series, and the cross polytope series, and the measure polytope series, or the hypercube series, and those are duals of one another. And if you look at that little table there, where I list as a function of the dimensions how many regular polytopes there are, then in 3 dimensions there are 5, in 4 dimensions are 4, after that it's all 3. So in a way, it seems like 3 and 4 are the really interesting dimensions, and we're lucky enough to live in one of those really interesting dimensions. Now, how do we make good projections of these things? Because we're in just 3 dimensions, and we start from a high dimension, like 7-dimensional object, and we lose 4 dimensions, we pretty much have lost all the information and all the essence. Maybe we can just kind of look at the connectivity. So it's sort of a game of making a model that has sort of the right number of vertices in the right constellation, that preserves as much symmetry as possible, and it avoids unnecessary crossings of edges that would only be confusing, because you then don't know is there a vertex at that crossing point or not. Okay. So let me look at the quick parade of possible reconstructions here. Let's start with the hypercube series. I really like the oblique Cavalier projections here. So we see the 3D cube up on the upper left, and then extruding that one below it gives the 4D, and then 5D is yet another different directions of doing an oblique projection, and 6D is one more thing. It gets a little confusing at this point, so maybe the right thing to do is change the scale of these oblique projections, right? And here I've taken 3 dimensions in 3 directions that make kind of, the regular cube, and then 3 more directions marking the other dimensions that are much larger in scale, and you get kind of a decomposition of the first 3 dimensions versus the other 3 dimensions. We simply sees, well, we kind of started to make the 4-dimensional simplex with a tetrahedron, and then we put a vertex inside. So we have something as symmetrical as possible, the tetrahedron, and then add 1 more vertex in the middle, and that gave us something quite nice. If we go now to the 5D simplex, we need 6 vertices. So we could say, okay, we still start with a tetrahedron, but then we somehow locate 2 vertices on the inside and connect everybody to everybody else. But maybe there's a more regular option. We could start with an octahedron, because the octahedron already has all the 6 vertices that we need. We just need to connect everybody to everybody else in the octahedron. Unfortunately, that gives us the 3 pink space diagonals which smash into one another at the centroid of this object. But what we can do is we can take the 6 vertices and warp them a little bit, and that kind of twists it in such a way that the 3 red diagonals no longer intersect at a point, but they're actually passing by one another as shown by the green light. This actually has the benefit that now the center is free, and so we can actually plop in 1 more vertex in the center in order to make 7 vertices in a rather nice configuration, and that would be the 6D simplex. And here would be a physical model of what that looks like, and I have a little yellow model there that shows that one. And we go on, we can go to sort of 8 vertices and 9 vertices. And again, here we start with an 8 cube that gives us 8 vertices in a rather nice configuration, but then we warp it so that the face diagonals do not intersect and the space diagonals do not intersect. That frees up the center, and then if we need indeed place a 9th vertex, the 9th vertex can go into the middle. It's kind of a game of making these models. I'm not sure that that tells you really all that much of what an 8D simplex really looks like. But I hope he's saying it a general idea. And in cross polytopes, it's pretty much the same thing. We have to place these vertices in some way. As we need 12 vertices in 6 dimensions, we could start with the ixahedral symmetry, but then we have to break it to get all these artificial intersections away. When we go to 7 dimensions, we need 14 vertices. Well, we can combine kind of a cube and octahedron, and again, we need to suitably warp it. But I don't want to go into more details here, and rather give more time to Hans to show us some more beautiful models.
So this is about the end of my 3D and 4D and hopefully never 5D involvement. I would like to kind of come to a place now where I can tell you how I make these things, how I come up with the ideas. And you already might have gathered that at least with these 4D shapes, I have an idea, I see a model of a 4D shape like a hyperdodecahedron. I make the sticks and I figure out which faces can I make and show as glass faces, as glass pieces. And you might, if you look carefully, there is this ring here of pentagons around this open face here, and there are two of them sitting back to back, and that would be these flying saucer things here. You might recognize those. So, but I do come up with models. Like in that picture, I built a paper model of a elevated icosahedron. It is not a stellated icosahedron. Stellating means to draw out the edges and make it star-like, and you can do that with some of the shapes, but not with all of them. Leonardo da Vinci came up with a way to make pyramids of equilateral triangles and put them on the faces. So this icosahedron has 20 pyramids of equilateral triangles sitting on it. So that's an elevation. He called it an elevation, not a stellation. And this lamp was built by, 75 students in 3 days. At a high school in Indiana. Paper model and the real thing. Another lamp that I designed and made at some point, and I also make that in schools, is a Pythagoras spiral, or Theodorus' spiral. Theodorus came up with the idea to take Pythagorean triangles and I have the next picture will be a little clearer. So the first triangle down here, the smallest one and the shortest one, has legs of unit. So let's say 1 unit, and 1 squared plus 1 squared is 2 squared. The square root of 2 is 1.41, and so on and so on. So the hypotenuse of that first triangle down there would be 1.4 something units. And I took that measurement and elevated that triangle by that much. So the next triangle has the 2 legs of square root 2 and again 1 unit, which would then be the square root of 3, 1.7, etc. And I raised that triangle by that number. So I came up with this whole spiral, but in elevations of it, and I could make it into a lamp. This is another lamp that I did with 75 students in 3 days in Indiana again. This was built, finished on the 20th of January 2017. And yes, I called it a disappointed small disappointed small stellated dodecahedron. And yes, the adults in that school got it. I just cut off the tips and inverted them, so just to make the lamp interesting. It's actually a beautiful piece. Tom Hull is a math teacher in Holyoke, I believe, in Massachusetts. And he is an origami artist and does all kinds of things, but he came up with this model, which is a compound of the frames of 5 tetrahedrons. What he did is he wove the frames together in this fashion here. They are not attached to each other, that's why I'm wiggling it. And this is not my design, I just made this model, and I made a few of them, and eventually I said, well, I can do this in glass. So I have a glass one as well, and that is a picture of that one. That's the glass 5 tetrahedron compound thingy. So there are, these are some other models that I made. Same thing. So, and here now we come to one of my favorite parts of this presentation. And I do need to wet my whistle. Remember the story that I told you in the beginning? Joshua taking up this thing and looking at it for 3/4 of an hour? You might not believe me, but he really did. This is another model like it. And you recognize a dodecahedron. I hope you do. And there is a cube inside. And this cube does not look as if it has flat faces. And you know, when you come afterwards and have questions and stuff, we can talk more about this, but it looks as if it is concave. It looks as if these rooftops, I call them rooftops, that are sitting on the face of this cube are inverted into it, are going into it, is concave. So the faces of this cube are seemingly concave. And he looked at this thing, and he looked at it, and then he walked away, and he came back after a couple hours, and he said, well, you know, the cube is not built with concave faces. The cube is a mirror. It's a very neat trick, he says. So, and then he looked at it some more and walked away again, and came back after yet another hour, and he said, and I figured out that there would be empty space in this cube. And he figured out what the shape of that space is. And I'm not quite sure how to do this from the front of a lecture hall, but there's a paper model here. And here is so here's my dodecahedron, and you can see the edges of the cube, right? The cube looks as if it has concave faces, so the cube in there looks like that, doesn't it? Same thing here. It's just easier to hold this. And I don't know, I can pass it around to a few people, and while I'm talking, you can maybe figure out if there's empty space in that thing or not. You know, can you feel it? Do all the faces touch all the way to the center? The corners, are they all collinear? So eventually he came up with the idea, you can keep passing that around. Eventually he came back and said, and there's empty space in there. There's empty space, and I know what the shape is, and I gave him a piece of paper and he sketched it out. So, I don't know, I guess I have to give it away, but this is the shape of the empty space in there. And this is my kind of proof. I feel like a street performer. Ta-da! So, but not enough with that. When I do this in schools, in classes, I travel around the country teaching this kind of stuff, math, this kind of way. I will ask the students, okay, can you come up with an algorithm for figuring out the volume of spiky? I call this thing spiky, which is very attractive to students too. So how do you figure out the volume of this thing? Just an algorithm. Which does not mean to have, you know, a finished. At that conference, the next conference after that one, I actually started giving out prizes for, you know, the best algorithm that someone could come up with at the conference. And there were people that gave me pages and pages of all kinds of stuff. I do not know to this day what they were doing. But I don't know. How would you figure this out? How would you go about it? You don't have to do any numbers. It doesn't have to have any units to it, just an algorithm. You take this and do that, and then you get this. Just very simple. The paper model can actually help you. Here you have the dodecahedron, right? And the dodecahedron has the cube inside. So what happens if I take the cube away from the dodecahedron? Yeah, come on. You have 6 rooftops, right? And these 6 rooftops have a volume. Now I can use the whiteboard. Yes! So, I'm learning. So the volume of the rooftops is the volume of the dodecahedron minus the volume of the cube. Does everyone agree with that? I showed it to you. I get a thumbs up here, good. So, but now I have the volume of the rooftops. What do I do now? I take the rooftops away from the cube. So the volume of spiky would be, what did I say? The volume of the cube minus the volume of the rooftops. Right? Very simple so far. Yeah? No, it's not.
It's just a mirror.
Yes. You are correct. But if it was built like it looks like it, then there would be concave faces. And so there's an optical illusion kind of thing going on here as well, yes. And I will build up on that, but it's a good question, very good. So what I do now is I plug this here into there, which gives me the volume of spiky is the volume of the cube minus the volume of the dodecahedron minus the volume of the cube. Am I still on the right track here? So, and what if I, pardon?
Don't go lower.
Over to the side.
Don't get lower, I'm sorry. So the volume of spiky then would be, if I reduce that, 2 volumes of the cube minus the volume of the dodecahedron. And this is my algorithm for figuring out the volume of spiky, the volume of this thing. And my students will come up with that eventually. You know, if I kind of goad them along and stuff, but that's how I would go about that. Now, there's empty space in the dodecahedron and cube. I have here the model of a rhombic dodecahedron and a cube inside. The reflections, this is a mirror cube in there. The reflections, though, look as if these pyramids that are sitting on the cube are going into the cube. And if you look at it, they seem to be going into the center of the cube. There is no empty space in that cube if I would build it with concave faces. So that's the second variation on this. And my last variation on that is this one here. And I do have a slide of that, but it's not really easy to see. Yeah, this is the paper model. We've gone through that. That's here we have the rhombic dodecahedron, and you can see that the reflection kind of meets in the middle. And here is this very model here. I couldn't figure out a way to show it any good in a photograph, but the reflection of these pyramids that are sitting on the faces of the tetrahedron seem to be going deeper into the tetrahedron than there's actually space for. So we have these 4 pyramids going into the tetrahedron but crossing over. There's not enough space. And that little JPEG next to it shows that somewhat. That was done for me at a math conference by the people that, by the SAGE people. He just did it like that. Awesome. So that's what I do with students. That's how I, kind of come up with ideas for things. I have here kits to build these models. If anyone is interested, see me afterwards. I don't want to peddle them yet. So, right? A few pictures of some works that I've done. That is a mural about 4 by 6 foot. Again, this is flat, it's 2D, but it looks like there are cubes. There is this, optical illusion in there, and these 2 hexagonals in there seem to be impossible cubes. If you look at them careful, you might notice that, the back of the cube is like in front of everything, and it shouldn't be, should it? It's like not right. So I made that into a clock, into a timepiece actually, and with 3 different clockworks, one for the hours, one for the minutes, and one for the seconds. So you have to kind of put your time together. That is hanging in a high school in Keene. Tom Longton, a digital artist from Bennington, Vermont, designed this trefoil knot. And it has 36 sections, and it is a Möbius strip as well. And the green one is, I think, in his garden. That was the first one I made. And this black one is at my house. It's about 2 feet tall. Looks very nice, I think. This is one of my most favorite pieces. In the 1960s, I believe, students from Great Britain came to the US, and in the rest of the world, we use the A4 format for paper, for writing paper, printer paper, and in this country, it's letter. And there's a difference. A4 is just a little bit taller and a little bit narrower than A4. And there are all kinds of things that I could get into now with these ratios. But there were strips of paper left. What am I talking about? No, I'm sidetracking. These students, one of them came up with what's called a sphericon. It's based on discovery by a Swiss geometer and artist, sculptor. And what he did is he took 2 cones, right-angled cones, and stuck them bottom to bottom. Cut them along the equators, cut them along the poles, and turned them 90 degrees. So he got what he calls a sphericon. And this thing tumbles. And then other geometers later on discovered what they call a hemisphere, where all the surfaces have the same radius. And this is about 2 feet diameter. The nice story about it is that I put it on eBay one night at 3 in the morning, and it was sold at 20 past 3. To a psychiatrist in New Jersey. The next day I call her, and she says, and I say, is that going to go into your office? She says, no. Like, no. Oh, okay, I'm sorry I asked. No, that was for a house. I think my last one here is just a few paper models. One of them you see here, this is the 5 Platonic solids nesting. It starts with the tetrahedron, the octahedron, the cube, the icosahedron, and outside the dodecahedron. And I hope that you will come and look. The other is a plain old dodecahedron. It is cut out with X-Acto knife, very meticulously over many, many hours by a student supposedly in the ADHD kind of category. You know, these really thin arcs that you see there, there are some really thin ones. He did not just, you know, draw with a circle a line and cut on either side of it. No, no, he drew parallel circles. Absolutely meticulous, phenomenal. And down below is just a paper model of 5 cubes intersecting. The fun thing about that is these 5 cubes fit into a dodecahedron. Just like these 5 tetrahedrons would fit into a dodecahedron. If you look at this, there's a pentagon here. There's a pentagon here. There's a pentagon there. And there are 12 of those. So you fill all the corners of a dodecahedron with these 5 tetrahedra. And that is the end of my part. Oops.
So a few samples how the regular Platonic solids are not just beautiful by themselves, but they're actually the basis of other things that have the same symmetry. And so we can essentially not just take, you know, the pentagons around the dodecahedron, but we can take instead pentafoil knots, okay, and place them in exactly the same kind of symmetry that you would see in the dodecahedron, and then you get something like this pentafoil tangle, where we actually have 20 of these pentafoil knots that interlink with one another. And so you can see that the Platonic solids go way beyond just their own polyhedral geometry, but they're essentially the foundation for a whole lot of beautiful objects that simply use the symmetries of these objects. Here are a few more examples. So this one would be icosahedral symmetry, and each one of the triangles of an icosahedron has been replaced by one of these trefoil knots. And it's kind of more complicated linking because each trefoil, as you can see, interlinks twice with each one of its 3 neighbors. We can also break the symmetry somewhat, and out of the 30 edges on the dodecahedron, we just use 20 edges and we link them up so there's one continuous path. This is called a Hamiltonian path that visits all the vertices of one of those surfaces. And then we can essentially put a soap film inside. We can dip this kind of warped thing, put it in a soap film, and out comes a minimal surface that would be a soap film. On the computer, at least, we can then poke some holes in it and some tunnels and make objects of a higher genus. Here is a tangle where we have 4 triangular bow-type loops that intersect with one another, and basically it has a twisted single bow tie above each edge of a cube. So there are 12 of them, and they come together in 4 groups of 3. This is a sculpture that I made for the 125th anniversary of the American Mathematical Society. And this now combines sort of 3D objects and 4D objects. Each one of those little triangular double pyramids is actually yet another rendering of a simplex. And so all the small simplexes together, they essentially trace out one of these bigger, you know, double pyramids. Okay? And so if you do the mathematics, there are a total of 125 tetrahedra in this sculpture. And that was the celebration of the 125th birthday of the American Mathematical Society. So maybe my final thing, I want to go back to Tiffany lamps, because that's kind of a theme here. You're probably familiar with regular Tiffany lamps. They're really beautiful, but most of them are just essentially half spheres or cylinders on the like. Wouldn't it be nice to have some more complex shapes, maybe tori or globes or something like that? What would happen if we go to actually higher genus Tiffany lamps? Now, in order to get the mathematical background for this last thing that I want to show, I have to introduce you to another mathematical problem, which is called graph embedding. Okay? So, in graph embedding, here's an example. Pat, Bob, and Alice live in 3 adjacent locations along the bottom of this slide. They all have spiffy cars and use them to go to Safeway or Blockbusters or the local gas station. But they don't like each other very much, and therefore they want their own individual private road to the 3 shopping places. And the road must not cross any one of the other roads. Unfortunately, this is not possible in a spherical world. As you can see, this is okay, but then Alice, she cannot place her last road. In order to make that possible, they would have to go at least on a genus 1 world, essentially on a torus world. Now, here is a much tougher graph embedding problem. This is the complete graph K12, where we have 12 vertices, and each one is connected to every other one. So it actually could be understood as a model of an 11-dimensional simplex. The question is, what kind of surface do we need in order to be able to embed that graph without any crossings? It turns out you need at least a genus 6 surface. And the most symmetrical solution I have found is this particular tetrahedral symmetry. It actually is like the edge graph of a simplex. Okay, there's the outer tetrahedron, all edges nicely rounded, and then there's the 4 spokes going to one side, all nicely rounded. This was made on a 3D printer and then hand-painted to distinguish the various countries, and the edges between 2 different colors are the original edges that we had on that K12 graph, and the black dots that you can see, these are the original vertices. And here is the same shape displayed as a virtual model using either shiny metal or colored glass. Now, if this were to be made from glass, then we could place 4 light bulbs into the 4 corners of the tetrahedron and turn this into a Tiffany lamp. And this is the kind of light that display that you might get out of this particular Tiffany lamp. Hans, any final comments?
Yes. Yes.
Yes. Okay, thank you for your patience. He's promising to build one.
A marvelous presentation. I'll moderate. There shall be a reception afterwards. I don't want to get between people and refreshments, but I've been asked to make a few announcements before the Q&A session. So in the foyer, you'll find a unique book enclosed in a glass display. The Pentateuch, the St. John's Bible, is the first completely handwritten illuminated Bible since the invention of the printing press more than 500 years ago. It's a journey through history with a modern twist. Magnified images of viruses under the microscope, strands of without a glass cage, and Christina Vanin, the Associate Dean at St. Jerome's, is here to answer any questions. That's the first item. There are 3 items. The second item, this Friday, March 10th at 7:30 p.m., here in the Vanstone Theatre, is the next lecture of the Catholic Experiences. The speaker is Father Michael Patella, Chair of the Committee of Illumination and Text for the St. John's Bible, Bugs in the Bible, an Intertextual Approach. The third announcement. So that's here, tomorrow. No, Friday. Thursday, April 20th at 7:30 p.m. at the Conrad Center in Kitchener. The Kitchener-Waterloo Symphony is presenting the only intersection concert this season, McEntyre. We saw the announcement of that before the talk, and everybody will have seen that. Now, some questions and some answers. Please.
You're saying that you have only 3 regular polytopes passed, but there's 5 is something you should be able to prove with discrete group theory, right?
What do you want to prove?
Group theory, with discrete group theory.
That's possibly, and if there's any mathematician in the house, I deflect that question to them.
The only reason I'm asking that is that you said that the way that you get the next one up is you deform that so that the body diagonals don't intersect. And once you do that, you do away with your symmetry, do you not?
Oh, absolutely. That's the point. If you have a 6 or 7 dimensional object and you want to make, a reasonable reconstruction in only 3 dimensions, you're losing everything. For instance, the 24 cell, which we both believe is a really beautiful one, in 4 dimensions, this has 1,152 symmetries. How much symmetries does it have here? 48. He lost all that. And the more you go up in dimensions, the more symmetries you will have. By the time you're down to only 3 dimensions, you have practically lost everything. In order to avoid these edge intersections, which I said, you're losing some more symmetry, and all you really get is the right number of vertices and the right connectivity between the vertices, but everything else is pretty much lost. So, you have given up 99% of all the symmetries in doing that.
They're not regular?
Oh, not at all. No, in 3 dimensions, I mean, they're in a way much, much less regular than anything you could do. Just like 1152 down to 48, okay? And as you go to 5th dimension, 6th dimension, it gets worse and worse.
I'm reminded that we have microphones for the questions, so that on replaying this lovely talk, the questions can be heard as well as the answers. So I would invite individuals with questions to please proceed to to one of the microphones. Benoit?
So I've seen, we're recorded, so this is perfect. Was that an actual challenge that was issued? Just for the record, was that a challenge that was issued, and are we expecting to see an answer to that challenge?
It's mostly a challenge.
Yes, it was a challenge. A challenge. I like it, though.
If the Faculty of Mathematics at the University of Waterloo wanted to commission such a Tiffany lamp as a 50th anniversary piece, would that be something that you would be willing to consider?
Oh, yes.
All right.
Oh, yes.
So, yes, question please.
This might be kind of a stupid question, but what exactly is a genus? You were mentioning
What is genus?
Oh, I'm so sorry. Genus is essentially a measure of connectivity of a surface. A blob, a sphere, a potato, they're all genus 0. A donut would be genus 1. A coffee cup with 1 handle would be genus 1. And then if you have a disc with 3 holes, that would be genus 3. So higher genus essentially means there are more ways how you can curve around. And because of the extra tunnels that you get in a genus 6 surface, you have ways of making crossings that you couldn't do in the flat, because one can go over and the other one can go under. So another genus 6 surface would be, this is, for instance, genus 5, right? Okay. And so on this, you couldn't quite map the K12. We can make simpler embedding problems. Right? Sorry, should I said that? Okay.
We have time for another question, if there is one. Please, David.
I was just wondering, glass, I'm not very familiar with the art. Is there soldering involved?
Okay. I'm using ready-made stained glass. I cut it by the sheet. I buy it by the sheet, and I cut out the shapes from these paper models. Pardon?
Not with scissors.
No. And no, you don't cut glass. You actually score it with a glass cutter, a glass scorer, but it is more difficult to say than glass cutter. So you scratch it, and then you break it along the scratch. you might want to grind the edge smoothly on a grinder, which is usually a diamond disc or a diamond pin that rotates. It is water-cooled. After that, you wrap copper foil, like Scotch tape made of copper, around the edges. And then and only then can you actually solder together. You put the pieces together and you put solder in there. Soldering is the lowest temperature way to connect two pieces of metal, in this case glass, surrounded by copper foil, which represents the metal. It melts at, I know it in Fahrenheit only, I don't know, 435 melts solder, and it solidifies at 375, so it is not overly hot. Maybe 180 and 150 or whatever it is, I really don't know. I only have American students, US American students, I should. Pardon?
The low 200s.
Yeah, something like that. So, well, the next hot way to connect two pieces of metal would be brazing, which is if you have, two pieces of brass and you connect them with a torch at 1200 degrees Fahrenheit. Welding would be still hotter. But soldering is the lowest temperature way to connect, and these silver edges are solder. That's how I connect these pieces. It gets interesting when there are three-dimensional shapes where I cannot get inside and fix mistakes. So I cannot make mistakes. And I think you can look fairly close at these pieces. But, yeah. So, did I answer the question? Yeah. I don't.
So we'll be having the reception now outside in the foyer, but if you wish to come down and take a look at these objects on the way, okay, they'll be brought outside to the reception. And also we've just learned one thing. Here on International Women's Day, we've learned of a new geometric shape, the Hemisphere. And so I think that's entirely fitting. Thank you again very much.